Okay, good. Couple logistics points first. One is the milestone is going to be due tomorrow. Okay, make sure it's a very low bar. Okay, so that everyone should be able to submit that kernel. Otherwise, you're in deep trouble. Okay, but go beyond that. Okay, make sure that you're on your way to be able to have 3 optimizations that you can begin to measure and write reports about. And Carl did a really good job showing you what we're expecting, right? So definitely use your time to make progress. Don't wait until the last minute. Okay, we set up the time, giving you enough time to be able to do a good job. Okay, so don't back yourself into a bad corner. Okay. Second one is the exam is going to be April 23rd and Monday evening, and I want to just quickly show a couple of things to make sure that the whole class is on the same page. So the most important resource you're going to have for that second exam is the study guide. And the study guide here is a little bit out of date. It was from fall of 2017. However, the only real kind of update that we need to do is to move some of the more recent exam questions into the study guide and give you a little bit more guidance. So that's what we're going to do in the next few days. Meanwhile, when you study, there are several things that you should do. We're going to first tell you the kind of topics that you should go back and refresh your memory. Okay, so these are the things that are general. We're not going to have specific questions about these things, but you really should kind of go back and review these a little bit so that you're proficient about it. And these were pretty much all tested in the first exam. And then we go into the more specifics that are going to be tested for the second exam. So the prefix sum, we stop at reduction for the first exam. Okay, so scan where prefix sum is definitely going to be a topic. So we'll give you some specific styles of questions, and just so that you can think about it more carefully. And some of these are actually similar to the MP questions, but some of these are not. Okay, so you should be able to work through these questions pretty easily. And then histogram. So these are the kind of things that are essentially, these really are just the simple applications of the lecture material, so that you can think through the kind of code that you write in the MPs carefully and clearly, right? So if you can, you should be able to work through these questions, and then we give you the answers. Okay, we even give you the answers and the explanation. Okay, so these things are really designed to to help you to sharpen up your thinking and your understanding. Sparse matrix multiplication, for different formats, think through the data structure, the size, the size, and any additional information you need to keep, and then memory bandwidth. How do you reason about some of the memory bandwidth, and PC system architecture. We'll give you some specific examples about use a particular generation PCIe. And then, if you need to transfer so much data and you want to accelerate by so much, you should be able to do a first-hand estimate about whether this is going to pan out for you, whether the GPU speed up is going to be so good that even after the data transfer and, with all the overhead, will you still be able to get significant speed up? And this also leads to a very important point of GPU programming. You really don't want to transfer data back and forth all the time. You really want to be able to keep the main data structure on the GPU, and you just keep launching kernels and then updating that data from the CPU side occasionally. But you really don't want to do the kind of data transfer all the time. And these questions help you to to really see some of these important points. and the CUDA streams, when you have some of these code, and what are the kind of things that you can actually execute in parallel. Remember, we have resource constraints, right? So if you only have one downstream copy at any point in time, only one stream copy can happen, right? And then if the code belong in the same stream, only one of the tasks will be able to execute at any point in time. So you should be able to reason about which actions will be able to go in parallel, which is not, and work through these questions, and so that you can you're really prepared, okay, for the exam. Okay, so we're going to the exam coverage is going to be pretty much until the end of the lecture today. Okay, and the Thursday lecture will be on MPI programming, and historically we don't cover a lot of MPI programming. It's considered to be a kind of a nice extension to the class, so that quite a few of you are going to learn about MPI programming for HPC, and this will give you that launching pad into using GPUs in clusters. So you should really pay attention to the topics that we have for the labs, and then use the exam in the previous 2 semesters. We give you those exams with questions, answers, and you will see the style of questions that we have for the programming code. Especially, we're really not interested in being tricky whatsoever, but we want you to be really, really solid about, given a particular goal, how do you manipulate the indices, how do you actually map those thread indices to the data indices, and how do you know that you're going to be able to get some locality out of these things. You should be able to think through these things with relatively simple programming assignments. The exam was a little long last time, so we understood it. So we're going to try to make it a little bit less long. But these things you never know. When we estimate the time, occasionally we can be off. So we were prepared to extend the exam time a little bit if we are off. So I told the TAs that we'll make sure that everyone will have enough time to work through it. The time should not be the limiting factor. Okay, so hopefully we'll have a really good productive exam on Monday. Okay, any questions about the exam? Okay, so let's go and cover the rest. There is one small topic that we did not finish from last time. Yes? Oh, interesting. Thank you. Wow. I was showing you all these things on the screen. Oh my. What's happening? Interesting. Seems like the display we may have to reboot the system. This is very interesting. Okay, I'm going to take some risk and reboot the system. Program audio. So somehow the projector was off. Yeah, we may need to reboot it, right? Mm-hmm. Oh. Okay.
Was it like this from the beginning?
Yeah,
oh.
Yeah. I think recording might be okay, but just students in this room did not see the projector. Were you able to see the images from the recording?
Yeah, I could see them.
Yeah, okay. Yeah. Okay, we're in business. Thank you. Okay, apologize for that. So next time, if something goes wrong, just kind of get my attention. I'm looking at you guys, and then didn't look at the screen. So you know what? Go back and look at the recording if you like. When I was scrolling through the study guide. Okay, so we were talking about memory coalescing, and then we stop here for the barrier synchronization. By now, you have used barrier synchronization quite a few times. The barrier synchronization is a very powerful method to make sure that all these threads are operating at roughly the same timing, so that you can control how they collectively use memory data and control how they can help each other in the shared memory and so on. So, as a review, it is an API function in CUDA, and all the threads in the same block have to reach the sync threads before anyone can move on. And this brings in a very important part of the semantics of sync threads. The barrier synchronization is a tricky thing, because everyone is supposed to reach that point before anyone can move on, right? But if you're not careful, if one of the parties that you're waiting for never showed up, you could end up waiting forever, right? And it's hard to second guess whether this person is going to show up or not. So if you go to a tour and the tour guide says, we're going to leave the bus, the bus is going to leave in 10 minutes, right? And invariably, if you have one missing person, people will go and look for the person, okay? And so, if someone is not going to show up, it's going to cause problems. So that's why when you use barrier synchronization in a kernel, ideally everyone in the thread block should show up at the barrier. If not, then we have a very problematic situation, and this is called undefined behavior. So if any thread may not show up in the barrier, the language will tell you that this is a situation where we actually don't know what's going to happen. Okay, there could be some, undefined behavior. The hardware may essentially have a deadlock and wait there for the thread to show up forever. Or the hardware may have an implementation that says, after we try a little bit, and if the thread still doesn't show up, the hardware may progress. So, but the important part is the interface tells the programmer that if you use a barrier synchronization, all the threads in that thread block better all be there or none of them will be there, so that either all of them will wait and proceed or none of them will wait there, okay? If some of them show up and some of them don't show up, it's an undefined behavior situation. And bad things can happen, good things could happen, but it's a very, very shaky situation. Don't go there, okay? Don't try. So that's why we always tell people that, if you go on a tour and the tour guide tells you that the bus leaves in 10 minutes, just show up, okay? Don't get into a situation where someone will have to come and look for you and eventually give up, and then you need to find a taxi back to the city, whatsoever. That's just a bad situation. Don't go there. Now, so we all know that these threads have different timing and so on, but here is a situation where some of the threads may not show up, okay? So let's say we use this barrier synchronizations, sync threads here, and this is the reduction, the reduction loop. So, we have a loop where the threads are going to be, gradually dropping off, right? Gradually dropping off from the execution. So we're doing that reduction tree now, right? So if we put a sync thread, inside the for loop, and that's okay. On the other hand, you know what, if we start to have, you know, let's say, we put the sync thread in the if loop here. Remember, this if loop is where all the threads are going to drop off. Okay? More and more and more of the threads are going to fail that test and not execute. So if we put a sync thread here rather than here, conceptually it might be okay, because in our mind, only those threads who are active in this piece of code really care about that data, right? So only the threads that are still active need to wait for other threads to finish the previous iteration. If they don't show up, they don't show up. So that's one way to think about this. But if you think about the hardware implementation, the hardware, it doesn't know that intention, okay? The hardware does not have the ability to read your mind. So that's why if you write the code like this and some of the threads don't show up, right, into this if statement, and therefore some of the threads may not execute that sync thread, then we have an undefined behavior. So in some hardware, the code might actually work. Okay, it's because the hardware has some implementation, decisions to make sure that when these things happen, they can still continue to execute under some assumption about the user intent. But these things will change from hardware generation to hardware generation, and your code may suddenly stop working from one generation to another generation when you have this kind of usage. So this is why we always tell you not to put sync threads into inside an if statement or a loop where not all the threads in that thread block will either all participate or none of them will execute. Okay, you have to make sure that if you put something, a sync thread into an if statement, then it better be all the threads in a block will succeed in the test, or all the threads will fail in the test. Okay, so it turns out that in the previous semester, a few students actually did some tests, and indeed, in some of the generation hardware, this piece of code can actually work. Okay, so you know what? But it will not be. This is something that you really shouldn't do if you want your code to be a piece of good code that will continue to work from generation to generation hardware. So this is also a story that I always like to tell in my 411 class. Since I haven't been teaching 411 for a while, I just tell it here. For many years, Intel architecture has these bits in their registers, in their status registers and so on, that are not used by the hardware implementation. Okay, you always have situations where you have, let's say we define a status register, and some of the bits were actually not used by the hardware. And they tell people not to use those bits. Intel will tell you, don't go mess with these bits, because future hardware generations may use these bits for certain purposes. Sure enough, some clever people, we have many, many clever people in the world, they realize that they can steal these bits, right, and then use these bits underneath, and without any consequences for the current generation of hardware. So they actually ended up using some of these bits, and the usage of these bits creeped into the open source software. And eventually, some of the open source software, even some proprietary software, start to depend on the particular way that these people use the bits in the Intel architecture. So as soon as Intel start to produce a new hardware generation that need to use those bits for some other purpose, it will break these hard software, okay? Because those bits no longer behave the way that these people saw in the previous generation. And Intel gets blamed for breaking the software, when they introduce a new processor. So Intel actually used to have this program, and being recorded, so I'm going to be a little bit, I would say vague. They will go around to some of these software providers and tell them that the way that you use these bits are not right. We know that you're using these bits, but the next generation processor is going to have to use these bits for the purpose that we reserve them for. So your software is going to break. How much money does it take for you to change your code to be able to, to avoid this problem? So you know what? There are many conversations like this happening in a big company, and ARM is beginning to get into that kind of situation and so on. So this is the kind of the equivalent in GPU. Okay, so the GPU architecture has these semantics, and then you're supposed to go with it. But people kind of realize that sometimes when you write these a little bit shaky code, and it still works, and they say, oh yeah. So that I'm so clever. The problem is, in a few generations, your code may not work anymore. So that, this is something definitely to remember. So that's why it's a bad idea to have sync threads in an if statement where some of the threads in a thread block will execute and some of the threads will not. Okay? So this concludes some of these performance considerations and so some subtleties in terms of using these important API functions. Now let's go into a topic that I'm going to introduce into the world of higher level programming interfaces for GPUs and parallel computing. So today we're going to look at OpenACC, and for those of you who are familiar with a programming interface called OpenMP, and these are closely related cousins. Okay, so if you know one, you will be able to do very well in the other. So what these are very similar interfaces. They're competing interfaces in many ways, and so I'm going to talk about the basic concepts and what we call the pragma types. It's a very different programming mindset. You're not doing the work in OpenACC by crafting the kernel yourself, by putting in the memory copy, memory allocation, API function calls. You're not directly doing that work. What you do is you instruct the compiler so that the compiler does it for you. And so I'm going to use some simple examples to illustrate, the concepts and functionalities. And this is OpenACC is a very valuable tool to quickly adopt GPU code into a large existing C, C++, or Fortran code base. Okay, and NCSA here actually has a fairly extensive program that that I lead to help the science teams to be able to adopt GPU execution into their large science applications. And more of these teams are using OpenACC to be able to at least prototype what the GPU how the GPU can be used, and then if they see some real opportunities, and they will actually use CUDA programming to get the maximal benefit. So it turns out that the programming, this programming model has a very interesting analogy. The analogy is when you have a project, do you do the project yourself, or you explain that to another person, the project to another person, and have another person to do the project? And many of the grad students, have complained to me that, when they supervise some undergraduate researchers, the most interesting complaint is that by the time I explain how to do this project to the person, I may as well have done it, right? That's a very common complaint. And I always tell people that, well, sooner or later you're running. If you're a single person, you're going to run out of bandwidth. So you may as well learn how to explain these things well, so that you can have a real team. But here, the relevant part is that the same thing applies. Sometimes it actually takes more work to explain what you want to do to the compiler, so that the compiler can do it for you, rather than you write the CUDA code yourself. So I'm going to go through some of these things, and you will also at some point you'll realize that there's actually going to be a trade-off. It's not that the compiler does the work for you, therefore it's always easier. it may or may not be always easier. Sometimes it's trickier to explain what you want the compiler to do, and you may be able to write the code quickly. So, what is OpenACC? OpenACC is a application programming interface, and it's actually a standard. So there is a standard body committee, committee that essentially defines what GCC means, and so OpenACC means. And when you write certain instructions to the compiler, how you should write it and what the meanings are. And OpenACC is consists of a set of compiler directives or pragmas. And then it also has a library of routines that the compiler can use, and also they have some environmental variables that can be set in order for the compiler to be able to set the execution environment for the applications. So these are this is the interface that people can use to write data parallel Fortran, C, and C++ programs that are run on accelerator devices, and both the GPUs and CPUs. You can actually generate CPU code out of OpenACC so that you can run multi-core, run the code on multi-cores and then vector instructions and so on. The best OpenACC implementation is from Portland Group, and the principal or the CEO of the company, Portland Group, is Michael Wolff, who's a graduate of University of Illinois, and he has a PhD from computer science from the CS department here. So as you go into the industry, you will meet many previous former students who are outstanding, who are really truly industry leaders and so on. So I think you will find your education extremely valuable, and just by looking at so many of the successful people in the industry from the university. And I say that with straight face because I have nothing to do with Michael Wolff's education. So he actually is one of my contemporaries. So he already graduated by the time I came to U of I. But these are the individuals that I really respect and admire. Okay, so OpenACC pragmas. So in C and C++, you can use hash pragma. Okay, that's a key word, hash pragma. To give the instructor, the compiler, information that is not specified in the language. So whenever you see a hash pragma, the compiler essentially takes the following string as a hint or as a directive, depending on the particular words that you use in that pragma. But if you look at the C and C++ syntax or the language specification, it does not have any of those things. The pragma is what we call a compiler specific. So the OpenACC compiler accepts certain way of certain style of pragmas, and so the compiler will tell you, if you use this is what it means to me, right? So that's between the compiler and the programmer, and the C and C++ standards committee does not control that. So the OpenACC API actually assumes an abstract machine model. So when you communicate with anyone else, there's always a mental model that you need to establish. So I don't know how often you have seen the situation where two people were talking like this to each other. So this person thinks that they're talking about let's say world politics, and this person thinks that you're talking about food for dinner. So you have these two people just talking across each other, and there's no communication. So the reason why is that they don't have a common mental model of what they're communicating. So here this is the common machine mental model that the programmer should have with the compiler writer. Okay, so the compiler writer assumes that if the programmer is expressing that pragma to the compiler, then the programmer is thinking about a host with a host memory, and then a device with device memory, and the host memory and device memory can have some kind of exchange through memory copy, right? So this is the kind of the model that the programmer and the compiler writer both have in mind when one gives instruction to the other, okay? So let's start with a very simple piece of code for OpenACC. So this is the beginning, and you can actually write this piece of code and get matrix multiplication to work, okay? And here is just matrix multiplication. So we have M and N are the input matrices, and P will be the output matrix, right? So we're going to first look at a piece of sequential code. So the sequential code will have for loop that iterate through the rows and columns of the output matrix, okay, the output matrix. So we're going to have the sequential code to iterate through the outer matrix and generate one element at a time, right? So this is the sequential code that we talk about before we talk about the kernel. So now, within each within each iteration of that doubly nested loop, we have the code to generate one output element, right? The output element, which is the inner product loop. So this is sequential code. There's nothing parallel so far, right? We have a three-level for-loop implementation. Outer two loops essentially enumerate through all the output elements. And for each output element, we have the innermost loop that does the inner product and then produce the result. So for OpenACC code, what we do is we can have a pragma. We introduce a hash pragma, and then we say that this is an ACC pragma. So the next word tells you which compiler should pay attention to this, because the same C code could be compiled by multiple compilers. It could be compiled by OpenACC compiler, it could be compiled by GCC, it could be compiled by Intel ICC. So each compiler has a different pragma. So this allows the compilers to tune in or tune out of these hints. So all the other compilers can just ignore this pragma, okay? And the way that I show you the code is that if you don't see any pragmas at all, a simple basic C compiler will be able to compile that three-level for loop and generate the correct code. It's just a simple C, simple C code. So now, when we add that pragma and ACC, then the OpenACC compilers start to pay attention. So this is the equivalent of, hey, Google, okay? You should know that, right? Okay, hey, Google, and then, yes? Okay, so then the rest of the line is the pragma text itself. The rest of the line is saying that the following code, the following piece of code is going, the loop, okay, the following loop is a parallel loop, okay? And what do I mean here? It means that outermost for loop, okay? And you will view the inner loop, two levels, as the body of the outermost loop. So whenever you say parallel loop, the compiler will look at the next loop, and it will see the outermost loop, that whole loop construct, the outermost loop, as a parallel loop. And it also tells you that you need to copy in the M and N matrices. So it tells you that, look, the M and N are going to be in the host memory. Remember that mental model? So there's a host, there's a host memory. So it says that M and N are in the host memory, okay? And you need to copy that into the device for this piece of code to work in parallel. And then after the execution, you need to copy out P. So P is going to be the result that needs to be copied from the device memory to the host memory. Any questions so far? Okay, so it will execute, it will generate some kind of parallel code, and it will execute the iterations of this outer for loop in parallel. Okay, So that's the concept here. Then you can add another pragma, an ACC, and say loop here. And remember, this piece of code is in the body of the outer for loop. So you are in the context of a parallel execution. So when you say OpenACC loop and you're already in a parallel context, okay, a parallel execution portion, then this loop tells you that the next loop will also have its iteration executed in parallel. So the result is going to be something along the lines of a x and a y, x and y kind of coordinate. And then we're going to probably have the outermost loop mapped to the y dimension, and the next level loop iterations mapped to the x dimension. So you have a two-dimensional parallel execution, going on. So one loop maps to one of the dimensions, and the other loop maps into the other dimension. So that's how we can get a two-dimensional grid going with the in CUDA. So essentially what this thing is doing is to say, let's abstract things a little bit. Instead of having the programmers to rewrite these two levels of loops into the kernel that you guys wrote and the kernel launch, we just tell the compiler that these are the two loop levels that I want to convert into a kernel, and then the compiler will generate the code. The compiler will generate the memcopy code, the CUDA malloc code, CUDA memcopy code, and the kernel launch code, and also generate the kernel body so that you would execute. Okay, so that's the basic idea. Any questions? Okay, yes.
Is that related to how you write your loop? Like, is there like a model you should follow so that the compiler can understand?
Yes, obviously. You need to write the code in such a way that the iterations across these loops are not dependent on each other.
Okay.
So right? Exactly. So, when you tell the compiler that these two levels of loops, iterations are these two levels of loops are parallel loops, you're certifying to the compiler that there's no dependence across iterations of either of these loops, or any combination of these iterations of these loops. So you could lie, okay? You could, but then the code will not execute properly. The compiler will just go and do what you tell the compiler. This is called directive. In a directive mode, the compiler does whatever you tell the compiler to do without questioning, okay? So it's up to you to actually have that loop body where the iterations across those outer two loops will not have any dependence. Okay? Any questions? Okay. We're going to actually go to the other mode, which is a hint. So whenever there's a hint, then the compiler will say, "Oh, I'll verify it." Okay. It's a different different interaction model. So there's some important observations about this piece of code. So the code is almost identical to the sequential code, right? I started by showing you the sequential code. So it was sequential code. And then except for the two lines with a hash pragma at lines 4 and 6. So the OpenACC uses the compiler directive mechanism to extend the base language. So the base language allows you to write a simple C program, sequential C program. And then the OpenACC pragmas allow you to tell the compiler, these iterations are independent, so why don't you rewrite them into a parallel kernel with the kernel launches and so on. So the pragma at line 4 tells the compiler to generate code for the I loop at line 5. This is the outermost loop through 16, so that the loop iterations are executed in parallel. And then the copy in clause and copy out clause tells you the data needs to be moved from the host memory to the device. It's copy in, and then device back to the host, copy out. Okay? So The pragma at line 6 instructs the compiler to map the inner J loop to the second level of parallelism in the accelerator, which usually means it's the lower dimension of your thread blocks. Okay. Now, so OpenACC programmers can often start by writing a sequential version. In fact, OpenACC programmers often don't even start by writing the sequential code. The OpenACC programmers often are given a piece of sequential code. So the most typical way is an application, the team decided to adopt GPUs. And then they say, oh, we have these millions lines of code, but we know that there's certain parts of the code that really are extremely time consuming. I'd like to be able to accelerate it. So why don't you take that piece of code, which is sequential, and then try to make it parallel by introducing some kernel code. And then so basically the developers will typically say, okay, before I commit and write these detailed kernel and so on, why don't I use some OpenACC to quickly introduce some parallel execution in there and then see if the trend is good. If the trend is good, then I put in a real effort and commit to a much detailed code writing, right? So the OpenACC code can typically be compiled by non-OpenACC compilers by ignoring the pragmas. You should be able to ignore the pragma and have any compiler to compile that C code, but occasionally programmers may actually make some changes to the to the loops. For example, to remove some dependencies across the iterations, and the way that they write the code may not work anymore for sequential code. But that happens very rarely, and you should try not to do that. So here's some interesting, frequently encountered issues about OpenACC. And some of the OpenACC pragmas are hints to the compiler, which may or may not be carried out. Okay? So the performance of OpenACC can depend heavily on the quality of the compiler. So a lot of times, when you say, go and do this, then the person will go and do this, and there may be more capable people, maybe less capable people, so you may have somewhat different results. But if you give less specific instructions, you say, in order to succeed in ECE 408, you might want to consider doing all the MPs on time. That's a hint, okay? And so some of you may decide not to do it. And so we're not going to say, okay, you're a bad person. We all have decisions to make in life. So those are the hints that may or may not be carried out. And as a result, in the exams, the scores can vary dramatically. Okay? And that's exactly what can happen here. And so some of the compilers may go and say, okay, it's a hint that this thing might be parallel. But when I go and do the analysis, because my analysis is not very accurate, I may not be able to tell conclusively that this is, all the iterations are independent of each other. Therefore, I'm not going to do it. Okay, I'm not going to do that transformation because this is just a hint. So it's up to me to ultimately implement it correctly. So I'm not going to do the transformations. And some OpenACC programs may behave differently or even incorrectly if pragmas are ignored. So that's another thing that I just talked about earlier. But these things are becoming less and less frequent because the compilers are getting better and better, and then the programmers are also getting more and more careful when they introduce the pragmas into the code. So the OpenACC compiler with terminology, the compiler deals with 3 levels of parallelism. It would have multiple execution units. So these roughly map to the streaming multiprocessors in CUDA, okay, in terms of the CUDA terminology. In terms of the CPU terminology, these execution units map roughly to the cores, the CPU cores, okay? And then every execution unit could have multiple threads. So these are the threading in CPU or the CUDA threads in the GPU, right? So thread blocks and in the execute sort of will be executing in the execution unit, and so you can think about execution unit roughly as thread blocks running on the streaming multiprocessors, and then the threads will be the next level, and then in the GPU, in the CPUs, you can also have every instruction can be a vector instruction, and then in the GPUs you will have warps that could be vectors, but in general, it's a little bit of a the GPU compilers don't really use vector instructions. They usually rely on the library to use some of these warp level, what we call the shuffle instructions. But this be kind of beyond the scope of this course. So, for the purpose of this 408, the way to think about it is that you have a host code. Okay, you have a sequential code execution until you hit a pragma, and then the pragma will trigger the compiler to be able to launch, these GANs that will be executing on the execution units. The GANs roughly correspond to the blocks, the thread blocks, okay? And then within each GAN, you will have these workers, and the workers roughly correspond to the CUDA threads. So you have the GANs, you have the workers. So each GAN consists of workers. So you have all these, all these thread blocks and threads executing, and some of them may be organized into these vectors, and then you execute. So then you eventually, this is essentially a kernel execution, and then you go back to the sequential mode, and then at some point, and then you launch another kernel. So this is one thing that we test all the time, because this is one thing that is the most commonly misunderstood and misused in OpenACC. Okay, this is what we call the parallel construct versus loop construct. So whenever you say the following for loop is a parallel loop, it's equivalent to say, hey, I'm going to the following region. So you use a squarely bracket to kind of delineate the next region. You say the next region is a parallel region. Okay, it's a parallel region, and then inside the region you mark the loop as just a loop because it's in the parallel region. So it's a parallel loop. Okay. So essentially here we have a parallel region that only consists of one single loop. So when we start to decouple parallel region from loop regions, so we can have parallel loop regions and parallel non-loop regions, right? And sequential and loop, sequential, non-loop. So the parallel construct will be executed on an accelerator, and you can specify the number of GAN members and workers, a number of, okay, it should be workers in each GAN, not works. So, this is, directed by the programmer. So, but the important part is whenever you delineate a region to be parallel, there's a very, very simple, important semantic. Whatever statement is in that parallel region, non-loop, okay? Whatever statement, non-loop statement that appear in that region will be executed redundantly by all the GANs and all the workers. Okay? So here, let's say we have an pragma ACC parallel, right? So that this region is a parallel region. But we don't have a OpenACC loop pragma there, right? So now this is a parallel region with only simple statements, right? Now OpenACC loops. So this A equal to 23 will be executed by 1,024 GANs, okay? 1,024 GANs, and each GAN will have 32 workers. So we're going to be generating 1,024 times 32 workers total, right? 1,024 of the GANs, and each GAN has 32 workers. So we have 1,024 times 32 workers, and they'll all will be created, and they will all execute A equal to 23 redundantly, okay? And the execution in this case will only be executed by the GAN leads, okay? So by the outermost loop, okay? So the redundant execution is, usually executed by one thread. So this is something equivalent to launching a kernel with thread blocks, and each thread block has 32 threads. And if you have a 8 equal to 23, chances are thread zero of each thread block will execute A equal to 23. Okay? Okay? So this is the semantic here. The reason is, remember, when we come into these, kernel execution, when you come into kernel, oftentimes we need to have, something like a collection of threads to load a tile, for example, right? And to be able to to execute some kind of assignment like I equal to the thread IDX times the plus the block IDX times block dim. Those are the statements that need to be executed redundantly across all the threads. So this is a way for you to be able to execute those kind of statements in the kernel that the compiler generates. Okay. Now, so here, if we have two loops here, the one on the left has the number of GANs 1,024, and it's ACC parallel. But did you notice that there's no ACC loop, right, anywhere in that picture? So this for loop is just treated as an ordinary statement. Okay? So this for loop will be executed redundantly by the 1,024 GAN leaders. Okay? But as soon as you mark this loop as an ACC loop, okay, GAN loop, what that means is that this loop will be divided up. The iterations of this loop, whenever you put that loop into an ACC loop status, the compiler will divide up the iterations because you're telling the compiler that the loop iterations are parallel with each other. And so the compiler will just divide up the iterations and execute some amount of it, a portion of the iteration with each GAN. And so the GANs will collaborate and execute all the loop iterations. So this piece of code will give you speed up, and this piece of code will give you many, many times of execution of the same code. It will not give you speed up. Okay? So you can also declare something as the worker, the worker group loop. So you can say the outer loop should be mapped into GANs, and the inner loop should be mapped into workers. So you will this way you will be creating a one-dimensional thread block, okay, one-dimensional thread block, and then the thread blocks will be executing the outer loop iterations, and then within each thread block, the threads will be executing the inner loop iterations, right? So this way, when you have a parallel outside and then loop, ACC loop inside, that means that the innermost loop iterations will be divided up. Okay, the loop iterations will be divided up into GANs and workers. So in this case, we will have 1,024 times 32 workers. Okay, workers, 32K workers, and each will be executing 1 million divided by 32K, which is 32 instances of foo, because we have about a million total repetitions of this food, right? 2048 times 512. That's a million, 1 meg. And 1 meg of these, execution instances will be divided up by the 1024 times 32, workers eventually, and they will be, each executing 32 instances of that food. Okay, so if you do it this way, you control. Essentially, the OpenACC developer still needs to have a little bit of a mindset as the CUDA programmer, right? When they think about GANs and workers, they're really thinking more, more or less the same as the thread blocks and the threads. The only thing is, it does not really set the thread block size. Okay, it doesn't set the thread block size. It doesn't really set, do the explicit division of, the amount of work. Whereas when we write a CUDA program, we need to set the thread block size, and we also need to take the data and explicitly divide it into the kernel launch, right? At the kernel launch stage, to create the right number of, thread blocks and, the number of, threads and so on in the execution. Here you just say that I want to have 1024 thread blocks, and then I want to have 32 threads. You, the compiler, go and look at the loop bounds and so on to generate the right amount of work, right, in each kernel, so that in the kernel there needs to be a little for loop that iterates 32 times. And that's generated by hand by a CUDA programmer, but here it will be generated by the compiler. Okay? Make sense? So here is a little bit more complex example. And we actually go over this in a book chapter. So, you have an OpenACC parallel region, so that the curly, the bracket region below here is a parallel region. And the parallel region will be executed by 32 GANs, right? Okay? So, if I ask you, how many times will statement 1 be executed? And you should tell me it will be executed 32 times, okay? Once by every GAN, okay? But once by every GAN. So you'll be executed redundantly by all the 32 GANs, right? On the other hand, as soon as you hit this loop, this for loop here, because you declare it as an OpenACC loop, the iterations of this loop and the n iterations of this loop will be distributed to the 32 GANs. So each GAN will only execute n divided by 32 iteration of that for loop. We come back out to statement 5 and 6, they will be redundantly executed, right? And then you see another OpenACC group loop, which is great, so that will be distributed. But if you look at, if it did not have that OpenACC loop GAN for that second loop will be redundantly executed by all the GANs. Okay, so that, once you understand this, it's very straightforward. But for someone who did not understand the model, the code can be extremely confusing and error-prone, right? Because you may not know exactly, what you're talking to the compiler about. So the kernel here, so far we have talked about directives, and here we talk about the hints. Okay, whenever you say a region is parallel, you're telling the compiler that that region is parallel. You can execute statements redundantly without any problem. You can execute ACC loops in those regions by dividing up the iterations and executing in parallel, no problem. But whenever you say kernels here, whenever you say the following region is a kernels region, it actually means that consider executing them in parallel, but only if you can verify that these things can be executed in parallel. So this is, this is why it's a hint. And it's actually, the usage of the kernel here is unfortunate, because the usage of kernel here seems like it's telling the CUDA programmers that these things should be generated into CUDA kernels, right? But really, the kernel, the usage of kernel here is the more traditional HPC way of using kernels. It is telling the programmer that this is a piece of code that will be very critical for performance, okay? And it's worth trying to execute in parallel because it probably processes a lot of data. It would take up a lot of time in the application. So try to parallelize it. So that's the traditional way of using the word kernel in high-performance computing community. Okay, so this is a little bit unfortunate for CUDA programmers. So if we mark a region as kernels region, then these statements in that region, in this region, could be executed in parallel. So the programmer can still do this. You can still say, this is an OpenACC loop. Okay, this is an OpenACC loop with the number of GANs. So you can distribute this loop into 1024 GANs. So now you have a pragma saying that, oh, I know for sure that this is a parallel loop. Okay, so do what I want. And then you can say another OpenACC, you can dictate it to be 512. But here it becomes up to the compiler. Okay, so if the compiler says, oh, this thing, if I do the redundant execution, it's going to cause problem because they may be writing into a common static variable or something. Then the compiler will break this loop out and execute it in strict sequential mode. No redundant execution for that for loop. Okay, if the compiler decides that any parallel redundant execution will jeopardize the correctness, it will break it off. Okay, so you can actually have a situation where you have a kernel region, and you have some pieces of code that will be executing in parallel, but then you will come back and could do the sequential execution for a while because the compiler decided that that piece of code in the middle can jeopardize correctness if you execute it in either in redundant mode. So some of you probably have have written Fortran programs. You can actually use OpenACC for Fortran programs. And there actually, believe it or not, there's still a large number of users who in the high-performance computing world that use Fortran programs, that write Fortran code. And in fact, this I think in the HPC world, the Fortran programmers are now being paid higher than C programmers because it's hard to find people who can write good Fortran code these days. So these things kind of just it's all about demand and supply. So that's what we're going to cover for OpenACC. Any questions about that? So I just want to make sure that you have a good understanding of the programming interface. You tell the compiler, the nature of the region and what you would like to do with the region. What you want the compiler to be able to to execute the statements redundantly, or you want the compiler to distribute the iterations of a loop into the parallel execution. And so the way to do this is through the parallel key, the parallel word and the loop word, right, in the ACC pragma. And you need to be careful whenever you use directives, because the directives tell the compiler that I know what I'm doing, do what I say. Okay, it doesn't matter what you think it is, do what I say. So if you have some kind of dependence and in your code that will cause problems, it's not the compiler's fault. But you will need to debug it since the compiler did exactly what you said, tell the compiler to do. And sometimes it can be hard to debug. The second one is, you can have a hint and you can tell the compiler, this is what I would like you to consider doing, because this part of the code is very time consuming. It has it has a lot of opportunity for parallel execution, but the compiler has to go and verify that there's no dependence, and the compiler is free to say no. Unfortunately, whenever the compiler says no, you may have a very significant drop in performance, right? So your code may not behave, may not give you the performance that you expect. So, and then the OpenACC compiler, need your hint about, the copy in and copy out. And if you don't do copy in, copy out, then the compiler will do the conservative way. So the compiler will say, okay, I think I need to copy this into the accelerator, but it may not be necessary. For example, that P, okay, that P is going to be generated in the accelerator and then will be copied out, right? But if you don't provide that copy out, the compiler may actually, still copy the data from the host to the GPU and then copy it back, even though the data will be overwritten, anyway, in this particular application, because the compiler may not be confident that all the P elements will be written by the code, right? The compiler may not be able to verify that. So that's why it's always a very interesting trade-off between how verbose you are in terms of telling the compiler everything about what's going to happen, what's going to be what's going to be needed, what's going to be overwritten, and so on, with these copy in, copy out kind of things, versus the performance. Because if you don't tell the compiler enough, the compiler may actually try to do some extra work just to make sure, and that would you can have lower performance. Okay, so this is what I was conveying at the beginning of the lecture. Sometimes explaining to a compiler or a person, what are the considerations? These are the these are the conditions, and these are the things I want you to do. It may be trickier than if you just go ahead and do it. Then they say, so what are the real reasons why people use this? One reason is this quick prototyping. But the other reason is actually more compelling, in the long run. The idea is that if you explain to the compiler the nature of your code and so on, so that the compiler can do it, the parallel for you, then when the next generation hardware comes out, when the next generation hardware comes out, the compiler can make those detailed code generation changes for you, right? The compiler may be able to generate, let's say that if the thread block size need to change, if some of the code, some of the data tiling size need to change, the compiler can do that adjustment for you, because that's part of what the compiler is enabled to do with all your explanations. Yes.
Is there a performance penalty for using these kinds of things? Like, how would you specify that you want your kernel to use like shared memory?
Okay. That's a great question. This is the reason why, when people really, really care about performance, they still go and write the CUDA kernels. Because, they are beginning to work into some of these more, in fact, even today, there's not an official version of OpenACC that allows you to do barrier synchronization. To tell the compiler that I want to do a barrier synchronization. Unfortunately, that's the first step to be able to use the shared memory and then do tiling, right? So essentially, there's some particular types of code that the compiler will automatically insert the tiles. For example, the matrix modification kind of code. The compiler is smart enough to be able to use shared memory, to be able to introduce the barrier synchronization. But there's no easy way for you to help the compiler to say, I want to use shared memory and I want to be able to barrier synchronize here. Okay. Any other questions? If not, this is really the kind of the point where we're going to finish covering in the final exam. Okay, so do yourself a favor, use the study guide, and also work through the programming questions that we had in the previous 2 exams. They're not going to be the same, but they will be testing similar things, will be testing similar concepts. So it will be helpful for you to work through those questions. Okay. So on Thursday, we're going to do 2 things. I'm going to talk about MPI, and also I'm going to spend a little bit of time, giving you more specific, hints about the exam. And then on Saturday, there will be a review session. Kevin is going to give that review session. And then on Sunday evening, there will be a special office hour. Okay. Meanwhile, use the regular office hours as well. Take advantage of it. They are still underutilized. So I really like to encourage all of you to take advantage of it. Okay. See you on Thursday.